So example 3 from chapter 7.8 on improper integrals. Now, just as a recap, improper integrals is going to be an integral where you have an infinity in there, some idea of infinity in the integral. So this is what our improper integral is. Okay? Now, if it's an improper integral, we're basically going to change that. We have to change that into a proper integral, for example, from t to 0, and take the limit as t approaches, in our case, negative infinity. Xe to the x dx. So we must change this improper integral into an area function and then take the limit of that area function. Now this idea now goes from negative infinity up to 0 of this graph. Well, when we take a look at this graph, it looks something like this. So it looks like the area or the integral will be some sort of negative value if it's convergent. If it's divergent, this will also be pretty much some negative infinity, right? So we are going to test that now. Is this convergent to a finite area, or is this divergent to infinity? Okay, so what we have to do is, if it's x e to the x, we're just going to integrate this just like we normally would any other integral, which means we do have to do a u sub. So, well, it looks like this is a integration by parts. So u is equal to x, dv is equal to e to the x, du is equal to dx, and v is equal to e to the x. So it's still the limit as t approaches negative infinity of uv minus v du from t to 0. So it'll be the limit as t approaches negative infinity of x e to the x minus e to the x from t to 0. It's a definite integral. The limit as t approaches negative infinity, yes, you do have to write it every single time, every single line. This will become 0 minus 1 when I plug in, minus t e to the t minus e to the t. Now, we did have to use integration by parts here, but now we're taking the limit of a function, which means you have to remember all your limit laws. This will just become negative 1 minus t e to the t plus e to the t. Now, if you take a look, the limit as t approaches negative 1 of a constant is just negative 1. The limit as t approaches negative infinity of e to the t, this one will approach 0, right? So this will be negative 1, and then this will be the only thing I have to worry about, minus the limit as t approaches negative infinity of t e to the t. Now, how did we do this? As t approaches negative infinity, this becomes negative infinity. This becomes 0. So right now, I have an indeterminate form of negative infinity times 0, which means, if you recall, we must use L'Hopital's rule. So L'Hopital's rule, you have to apply it to a fraction, so I'm going to put t over e to the negative t. Right here, I am going to apply from here to here, I should say, L'Hopital's rule. And then I will get the negative 1 minus the limit negative infinity of 1 over the derivative of this. Take the derivative of this entirely separate, which is negative e to the negative t. Now it's easier because the limit as negative, this approaches negative infinity, this becomes positive, so the denominator becomes infinitely bigger, which makes this 0. I get a convergent area of negative 1. So going back to that graph, that means this area right here is a convergent area of negative 1. Now in this case, example 4, it looks something like this, from negative infinity up to positive infinity. Now in this case, you are going to be doing a split from negative infinity to some constant, I mean, I would just pick 0 of 1 over 1 plus x squared dx plus 0 to infinity of 1 over 1 plus x squared dx. So I'm splitting a boundary, a constant of x equals 0 here. Notice there are no asymptotes here, so it's a continuous smooth function because this will always become positive. X squared will never be negative 1, which is the only way we'll have that asymptote there. So the graph of this will look something like this. And of course the question is, will this area converge or diverge? So what I've done is I've split the integral to find the area from negative infinity up to 0, and then from 0 up to positive infinity. You cannot do both at the same time. Which means if I want to write this and get full credit for it, I must switch it to an area function. So as t approaches negative infinity of t to 0, 1 over 1 plus x squared dx, plus the limit as t approaches positive infinity of 0 to t, 1 over 1 plus x squared dx. Okay, if any one of these turn out to be infinity, then this total area is divergent. Okay, if you take a look at your textbook, there is this example in your textbook. You can take a look at the answer. I think they only test one, and this one turns out to be divergent. This one turns out to be infinity. Therefore, the whole thing is divergent. Okay, so moving on to the next example is something that looks like this. Okay, so in this case, we're talking about an asymptote. We have x equals 2 when I plug it in. So let's take a look at what that graph looks like first. So the graph looks something like this, 1 over the square root of x minus 2. And we're taking the integral actually from x equals 2 out to x equals 5. So on this end, because on the right end I do have this very definitive barrier, it will be an area, but as x gets closer and closer to 2 from the positive side, we have an area that's same idea as that other asymptote, right? Where it looks like it's getting closer and closer to 0. Okay, the area is getting thinner and thinner and thinner here. But is it enough to say that this is a finite area, or is it a infinite area? So let's take a look at that graph again. So the graph was, there is an asymptote here at x equals 2, right? Because when I plug in 2, I get a denominator of 0. The graph looks something like this, and we're only taking it up to x equals 5. Right? So we are looking at this area right here. Okay, that's what this is doing here. Now again, this right here is still improper. It is still improper because of this value right here. We have some sort of infinity value here at x equals 2. So this is still what we call an improper integral. And that improper integral, we will be changing it to an area model, get rid of that improperness as t approaches 2 this time from the positive side. So we know how to take the limit as t approaches 2 from the positive side of the area as from t to 5. Square root of x minus 2 dx. Now in this case, so I want, as t is here, as t gets closer and closer to 2 from the positive side, we're looking to see if this area is finite or infinite. So as t approaches 2 from the positive end, we're going to be finding the antiderivative. So this is x minus 2 to the negative 1/2. So I'm going to add 1/2, right, divided by 1/2. This will give me from, t to 5. So this will give me the limit as t approaches 2 from the positive end of 2 times 3 square root of 3 minus 2 times the square root of t minus 2. Now, this is going to be a constant, so I get 2 square root of 3 minus 2 times the limit as t approaches 2 from the positive end of t square root of t minus 2. There is no domain issue here, so 2 from the positive end of square root is just going to be 0, so I do get the 2 square root of 3, so this is convergent. This area right here will be 2 square root of 3. Okay. Now, again, for improper integrals where you have a domain issue and that domain is one of your boundaries, then that is also considered an improper integral. I believe those 2 examples, or 2.5 examples, are enough for you to do all your homework. So that will be due by the end of class tomorrow. I think that's it. This is the other one. Oh, so this one. This one will be, again, the domain here. To make this improper, it would be improper because at x equals 1, right? So you would have to split that up to 0 to 1 of dx over x minus 1 and add that to 1 to 3 dx over x minus 1. And then, of course, because that 1 is what makes it improper, I'm going to switch out that 1 and go t is equal to 1 from 0 to 1 is from the left end of 0 to t dx over x minus 1 plus the limit as t approaches 1 from the positive end from t to 3 of dx over x minus 1. Now, if you don't split this up into its 2 integral parts, and you just take the antiderivative of x minus 1, you will get an error. You will get an area that is actually a mistake. So try this. Check your answer in the book. Wah! The homework will be numbers 5 through 10, numbers 27 through 32, which is everything that was circled. I will collect it 30 minutes into the class. And that's it. I will see you tomorrow, and then tomorrow we'll do the review.